How do juggalos work? There are 4 basic types of magnetism that a material can have. And all materials have some kind of magnetism. It's just that it's literally almost worthless because electrons primarily, but also other subatomic particles and also other particles. Superconducting only occurs at really, really, really low temperatures, and superconductors are repelled by magnets. You can also do this experiment with non-superconductor materials. It will also do this effect. It's also sometimes mistakenly called paramagnetism and that sort of thing. And this has to do with a reaction of a magnetic field next to a superconductor, creating a virtual magnetic field, or more accurately, really a magnetic field, reflecting back against it so they repel. You can also get the same thing if you get an aluminum tube or any other conductive tube like a copper tube, clean up the interior, aim it straight down, but you don't really have to, and drop a really strong magnet through it. It will slow itself down because it's repelling against every direction. Gravity is still dominant, but it slows it down. It's really weird. Diamagnetism. Diamagnetic materials are weakly repelled by magnetic fields for the same reason they're marginally conductive. And they're pretty common. Paramagnetic materials are weakly attracted to magnetic fields that are permanent. And lastly, ferromagnetic materials strongly attracted. So it's just a gauging of how strongly or weakly they're attracted or repelled. Now, I've gotten this backwards before. Paramagnetism and diamagnetism are very close to the median edge there. We use paramagnetic and diamagnetic material for shielding, and it has the effect of shunting or reflecting magnetic fields. Both of them can kind of do it for the same reason conductive pipes can reflect magnetic fields, and superconductors can be used to lift a train. Only certain materials at very cold temperatures can become superconductors due to electron pairing. I'm going to get to that in a minute, and other characteristics. All right. This has to do with what heat is. Heat is the vibration of molecules, but there's other forms of heat or other forms of electromagnetic radiation that you can detect or infer, even though we're not talking about that, we're talking about a mechanical characteristic at higher frequencies, which involve the electrons moving from shell to shell and vibrating. If you can get them to stop doing it and having them do a paired round the rosy, or a grouping of them in a like this, you can force them to stop being a cloud around the atom and to be a disk. Or not a disk that squeezes out, but the same size and be like this. That means they get a crop top. So here we go. All materials experience diamagnetism, including skin and flowers. It's a very weak effect, so we don't notice it in everyday life, and it is the one that causes things to be repelled because all atoms, unless they're ionized, have electrons. And all materials have these mostly unpaired, unorganized electrons. And if they're exposed to a magnetic field, they will then very suddenly go from this to snapping a little bit like a donut and attempt to be a magnetic field. Or attempt to be a field of electrons going one direction or the other. They either go the same direction and attract, or the other direction and repel, based on pairings and based on chaos theory. Many materials are paramagnetic, such as oxygen and tungsten, but it's very weak, and this is where it's very slightly attracted to permanent magnets, or any magnetic field. It doesn't have to be a permanent magnet. It can be a coil of wire with electricity going through. It's based on the electrons. Next. Since all your atoms have electrons, and everything in the world has electrons, all that has to happen is that the electrons can sustain one direction, or they cannot. Or they will sustain an opposing direction, or they cannot. Or they're in pure chaos, or they can become just slightly more organized. All the electrons orbiting an atom can go any direction in any pattern. But if a majority of them, only a slight, sort of like a voting situation, can go one direction versus the other, even though the others are going the opposite direction, it will become magnetic. And if most of them are going one direction in a molecule, such as iron oxide or something, then the electrons can trade between atoms, and that gives them a pathway where they don't have to fight with each other within each atom, and it will in effect have a net effect of creating a magnetic field, because electrons moving in a circle cause magnetic fields and vice versa. While we have a particle, a physical particle for the electron moving, we don't necessarily have an answer for what the magnetic field truly is. It's an effect. That's as far as we can pull it until you study electromagnetism. Ferromagnetism, only a very few elements are ferromagnetic, just like only a few of them are superconductors at any temperature at all. You have to combine them into compounds to get them to be a strong magnet, really strong, or use rare earth materials in combination, or to be a strong superconductor. This includes iron and cobalt and nickel. They're the only types where magnetism is easily observed in daily life. So there's a huge amount of this where, unless you're at ultra low temperatures, you don't experience any of these magnetic fields, so we see lodestone and other elements. Above a critical temperature known as the Curie temperature, magnetic properties disappear. Magnetism at its root arises from just two sources, and at higher temperatures they're disrupted because the molecules become chaotic, so they can't share electrons between each other, and instead of going in a figure eight, go in a circle, they start going into figure eights in different dimensions, pointing different ways, because they become chaotic. At low temperatures, the chaos is reduced, and at mid temperatures, whatever it is for that element, it's also less chaotic. Chaos gets rid of magnetic fields. Organization causes it. We're going to get to a nasty outcome if you want to know about it. All of this is based on magnetic moment induced by the spin of elementary particles. Now that may sound really hard to deal with, but the magnetic moment is referring to the effect of something causing a magnetic effect. So the magnetic moment should just be changed to the magnetic effect and strength level is induced by the spin of elementary particles. That can be that they're spinning on their axis or that they're orbiting. That's their spin. It can be either. Inside of most atoms are neutrons and also protons. A proton in movement can technically cause a magnetic field as well. High temperature plasmas sometimes have magnetic effects. They don't actually sustain a magnetic field most of the time, but it's kind of like that. By having a plasma, you've stripped off the electrons. You just have the neutrons and the protons. Light gases like hydrogen can be stripped almost entirely of electrons, and it becomes a proton-based field that can also have a magnetic field. It doesn't react the same way everything else does, because even room temperature stuff that hasn't been ionized with electrons, again, can have an atom to where the electrons are literally mostly moving in one direction, on one axis. Mostly. It can be complete chaos, but most of them are moving this way. Also, individual atoms next to each other can share one electron going this way, and if it just goes one direction, it will cause that. And charges between atoms or between molecules that are near each other could also reinforce each other. And the net effect is a magnetic field. Even if they oppose each other, they can alternate back and forth and just have a net effect of an odd number pointing north or pointing south, depending. Other things it's based on are the names for it. I'm just going to leave a bunch of links below because that's really what causes this. Elementary particle electron spin moment, electron magnetic moment, spin magnetic moments, and any other elementary particles that can create this effect, or just an electric current, a coil of wire. Once human beings were able to run electricity through a coil of wire and create a temporary magnet, that became the model for what can happen inside of an atom. If you make a coil of wire wrap this way and run electricity through it, it'll form a magnetic field depending on which way the electrons are now moving. If you wrap it in a sphere shape, it's going in every direction at once. It won't normally form a strong magnetic field in one direction. It may form multiple magnetic fields. They go all over the place. See also the sun, or a few of them that don't seem to match up correctly. See also the Earth's magnetic field having defects in it over large areas. But on smaller areas like molecules, the electron spins normally end up either effectively flipping the coin and going Trump versus Hillary magnetically. And remember, it wasn't a briefcase, it was a pencil box. Next. Magnetic moments in the nuclei of atoms are typically thousands of times smaller than the electron's magnetic moments. Translation. the core of an atom being mostly protons and neutrons doesn't really have as much of a magnetic effect. In fact, it can't. It's 1,000 times weaker than the electrons in the outer shell and the inner shells all combined, even if they're in chaos. So it's almost not recordable, but like I said, it could exist, and it has experimentally been done. They're negligible in context of the magnetization of materials, because materials either become magnetized or paramagnetized or superconducting or diamagnetic or ferromagnetic based on these things. If you have an odd number of shells, maybe that causes it. Or an odd number of electrons, and certain electrons just go one direction or another. Electrons combining into pairs with opposite intrinsic magnetic moments, or combining into filled subshells with zero net orbital motion. What that means is the shells cancel each other out, or the electrons in the same shell are also spinning on their own axis against each other and cancel each other out. See also the gyroscope effect of inertia, and why you don't stick a counter-rotating gyroscope on your bicycle if you want to stand up. And also the shells could be all going the same direction, or they could be going opposite directions, nulling each other out. But it only has to have just a slight imbalance for you to get some magnetic effect, or a major one. And you can induce it by driving it with a magnet and disrupting it mechanically if they're big molecules like iron, or heating it to the Curie point and then having it aligned now to the magnetic field. See also the magnetic earth. Point your sword north, heat it up in the fire, and let it cool. It will become a magnet. Also make sure you get the angle right. Yes, there is a tilt to the magnetic field. It is often the case that various electrons in the solid will contribute magnetic moments that point in different directions, random directions, opposing directions, so that the material will not be magnetic no matter what is done with it, or it may be completely immune to it, or only temporarily doing this. See also the fact that if you get a strong enough magnetic field, a neon sign will start turning off the flow, and see also that electrostatic charges have a much stronger effect in a vacuum tube than a magnet, most of the time, per unit of energy. So your old TV set had coil magnets on the outside of an electron tube that had deflectors that were really close to it that used electrostatic charges, or just simply potentials. But the magnetic field had to be hundreds of watts in some cases, compared to a couple of milliwatts to drive the electron beam. See also oscilloscope. Thank you for watching. Have a good day. Good luck with that. Bye-bye, Juggalos.